Okay.
Hello, everybody. Good evening, good morning, wherever you are in the time zones. We are here again with another session of in NXP Campus Connect platform. We would be recording this session for the benefit of all the people. So, if anybody has any objection, please raise your hands now. Rahul, any objection from anybody?
No. Akhil, please continue.
Okay, so yeah, please record the session then. Okay, so today we have a very insightful presentation on analog design from two of our experts in NXP. We have Mr. Jaideep Banerjee and Mr. Abhinav Dikshit. Jerry, both of them have close to 20 years plus of experience in analog design, and they have been instrumental in designing a lot of analog circuits like the PLLs, VCOs, and band gap references for our chips in NXP. I would like to welcome Abhinav and Jaideep on this forum. So Jaideep, please take us through the journey of analog design.
Okay, thank you, Akhil, for the introduction. So I hope everybody is able to see the slides. Unfortunately, my webcam has some problems, so you will not be able to see me, but Abhinav will be there. So me and Abhinav will go through these slides on analog design, why it is important, and basically what it takes to become an analog design engineer, what are the specific IPs and analog blocks which are used in modern days chips or system on chips, that's what we call them. So let's start. Okay, so this is the agenda. The first will be the what is the importance of analog design. Then I'll briefly dwell upon the analog and digital subdivision in modern SoCs. Then we'll describe what is typically a characteristic of an analog system and a digital system. Fourth will be interest of you. This is basically what I call the body of knowledge, or fourth section, what all the areas you need to know or the skills you need to develop if you want to work as an analog design engineer. Okay. Then we will describe some in somewhat more detailed typical analog blocks which are used in modern SoCs. Then we'll describe the future trends in analog and digital design. Okay, and then finally we'll show a few slides on NXP products which are NXP analog and mixed signal products. Okay. So the first question is, if you look at the media, everybody that talks about digital from digital devices to digital marketing. So and there is a view that analog is something old, something outdated. But the reality is, if you take any product which you think it is a digital, let's say a very ubiquitous digital product will be like a cell phone or a laptop. It has to be used by humans, right? So you have to see the display. The display is analog. The motion, it has to be turned on. You need power supplies for that. That is analog. Okay. So to make any system, any electronic system or any subsystem usable, either for humans or for machines or industry or any place, you need analog signal at an interface and to make it work. Because any chip, let it be a latest Intel processor, it still needs an IOs. It has to interface with the external world. It needs clocking subsystems. Because digital circuits are you may have a very complex core, but still they are synchronous at heart. You need clocking subsystem, which is a part of analog design. Okay, and you need power supply, because without power supply you cannot work, which is again an analog subsystem. So this is a block which typically a system. If you pick up any chip, it's actually like this. You have an input sensor. Basically, it can be a transducers. Then you have a transducer. Then you have an IO ports. Then you do some kind of analog signal processing. Then it goes through a analog to digital converter. This is where the bulk of digital things happen in the digital processing. But then to make this digital processing work, you need power supplies and you need clock. And then again, to make to make the use of output. Let's say if you are listening a song, it doesn't matter you are a fan of Ravi Shankar or Jimi Hendrix. You cannot listen it to 1 and 0. You have to listen into human usable form, so you have to, again, your ears are analog in nature, so you have to again convert it into analog output. So that's the picture, right? Is so to make a digital system or any system work, you need analog. So the way system is integrated, so this system either can go into if you see a typical board, modern day board, it is like this actually this diagram is valid for board or any modern SoC system on chip design. Okay. So typically, this is a kind of a top level, functional division of analogs, any chip, any SoC. Okay, there, depending on application, you may have, the area of digital might go up, or there are some application where the area of analog goes up, and then you have an IO. So there is, in reality, there are no pure analog or pure digital chips. It's always a mixed chip, which mixed design, or there are no pure analog or digital boards. The system are in reality always mixed. That's what I wanted to convey from this slide. Okay, so this is a very brief. I believe most of you know the typical characteristic of digital design is that it works in a two-state system. It's a one, or logic 1 and logic 0. So essentially, you have a vector of input which are 1 and 0, and vector of output 1 and 0. Okay, so you can support multiple IOs. So easier. The biggest advantage people ever invented digital system was because the big thing was it has a very good noise margin. And then there are other advantages when you do if you do a digital system. There are a lot of tools, and there are a lot of automated system which helps in designing the system. So basically that's why you see a lot of digital systems coming up in the marketplace. Again, from the analog characteristics, again, it is a bit different. There you need to take care of, you need to take care or understand transistor, resistors, current versus voltage characteristics. Okay, so output is in digital system, output is always discrete in nature. In analog system, it can be discrete or continuous. Okay. Most of the system are continuous, but there are also discrete systems which are analog in nature. Okay. There are challenges of analog design is like this more complex to design, to do a basic analog design. There are very little automation tools. The only automation tools I've been working in industry is largely basic, is a schematic. What I've seen is schematic entry and simulation support. Most of the other task is manual most of the time. Now there is a noise margin is poorer. In principle, you can when I say noise margin, you should always consider in terms of power. So why noise margin is poorer? Because if you want to improve a noise margin of analog system, it can be shown. It's not very hard to show, but it is like you need to burn 4x power. But a digital system, increasing a signal to noise ratio by 2x, you need to just add 1 bit. That's the one huge advantage of a digital system, and that's why the digital systems were invented in first place. Okay. Second, and one of the thing, this is very specific to SoC design. Basically, we make upgrade our technologies every 3 to 4 years. Now, the most of the digital system you can reuse it. It's almost like a software code, and there are tools which translate it to silicon. So a lot of reuse is possible in digital, but in analog, it's for all practical purposes, it's a redesign every time. Okay, so typically, this is analog subsystem in an SoC. So you have a timing, as I said, for any chip, whatever be analog, digital, a very high-end processor, you need timing, you need power, and you need IOs. So these are the typical analog subsystems which goes into SoC. It's a timing or clocking subsystem, the power management, data conversion, A to T, D to A. Basically, that's what I said. Now, these are interesting, like high-speed transceivers. So I believe everybody must have used LVDS or USB or HDMI in their life, and they are considered digital system. But I'll come to the slide. This is not really a pure digital system. They are actually a mixed signal systems, and rather complex system at that. And then there are like RF, which are important for mobile and other communication. And of course, and there's analog front end. Basically, you need some kind of analog signal processing before you give it to a digital processor. Now, these are very important slides, particularly what I call body of knowledge. If somebody wants to get into this field, so in this next few slides, I have captured what all the areas you need to concentrate on, and what are the skills you should develop, okay, as a student. So first thing is you must know basic circuit theory. I've given an example of Van Valkenburg's network analysis because I studied many years back from this book, but there can be equivalent sources. I believe there is engineering circuit design, or there are many various books, but that's what. So you need to know the time and frequency domain of behavior, basic circuits like inductors, resistors, capacitors. This is fundamental. So okay, this slide just captures it. So you need to know the basic voltage current characteristics of these devices, okay, because these are the building blocks of all analog blocks. Okay, next thing you should understand the diodes, BJTs, MOSFET, particularly MOSFETs, because most of the chips will be built on MOSFET in these days. So MOSFETs are important, but we do still use sometimes diodes and BJTs. So you need to understand this area. Typically, you will the level of Cedra Smith or its equivalent. You should also understand, what do you mean by small signal? It is basically a perturbative model. So you have and I've also included some other references, like there are excellent sources of a series of lecture by Behzad Rezavi on the level of and it follows his book on microelectronics, which is very similar to in scope to Cedra Smith's book. So basically, you should understand basic amplifier, IV characteristics, what do you mean by small signal model, and how to calculate gain of a very gain of any typical amplifier structures. So here I have just captured a basic small signal model of what is called common source amplifier. Okay, and very similar. You have a very similar model if you consider a bipolar common emitter model or amplifier. Okay. Another very important area is feedback and stability, understanding of feedback and stability. Okay, so you will be surprised. I mean, when I was undergrad, I really did not understand why we were taught Bode plots semester after semester. But trust me, you will be needing that in industry if you want to get into analog design. And you will be using Bode plots almost every week for as long as you are in this area. Okay. So here are some of the, and again, when I say feedback system, there are digital feedback systems also, and in fact there are some analog blocks. There are particularly some modern analog power management systems where people are developing product and doing research with digital controller. But and if you see some high profile cases like Mars rover or recent lunar motion, they all use digital control. But there's the thing with digital control is that it is workable where your input signal or things which you are trying to control moves very slowly as compared to your controller. If I go to this picture, for a digital system to work, the input should be much slower than much slower than your feedback loop. Now the thing is, what differentiates it into it with a typical analog feedback is that analog feedback is works at speed. So let's say if you have a if you have a 100 megahertz system with a signal which is coming at 100 megahertz, which you want to control at digitally, you need you need at least 1 gigahertz feedback loop. But the thing is that if you however in analog system, it will be at the feedback works at speed. So if you really can build a feedback at 1 gigahertz, you as well build an amplifier of 1 gigahertz, because surely you can find the application of 1 gigahertz. And one of the this I have included a very good online resource. These lectures were recorded by Dr. James Roberge from MIT way back in 1985. So it's a very good resource. You can check this link. This was and this has a series of lectures, and this slides of lectures are very the way he has put this. The control theory is very relevant for analog design. So you get a book, you get a series of 20 lectures, and also lecture notes. So that's a very good resource. Again, another thing you should understand is for signal processing, basic signal processing like Fourier Laplace transform, because these are fundamental. Again, these are fundamental, and we use it every day. A good reference may be like a signal system by BP Lati or Oppenheim. Okay. And of course, there are a lot of web resources these days available. And one more thing you should understand very well is digital design and concept, because as I said again and again, most of the actual real system are not pure analog, not pure digital. They are mixed system. So there is always a strong coupling between analog and digital system. They affect each other, and for your design or your system to work, you should need to understand coupling. And moreover, most of the analog circuits today, and when we come to the trends, you will like particularly in data converters and power system, you will see that a lot of analog designs are actually digitally assisted, like issue, because one of the problems with analog design is that it has over digital design. Again, this is again related to noise margin and other issues, is like component variations, which are now these days possible to fix digitally. Okay, and a good reference is again Morris Mano, and there is another good web resource by Professor R. Srinivasan. He was ex-professor from IIT Madras. So there he has a kind of 50 lecture series on digital system design. So this is basically these things I have captured. You should understand these areas like the network theory, the transistors, devices, signal processing, and digital design at this level to enter into analog design field. Okay, so next I will capture in somewhat brief detail on typical analog subsystems which we work on. Okay, so we'll start with the clock generation. Now, if you see most of the SoCs, you need multiple clocks. Most of the SoC work like core works at 1 gigahertz, maybe IO works at 100 megahertz or so. So there will be some subsystem within a SoC which will work at, let's say, 400 megahertz. So depending on protocol and how it is working, you will see multiple clocks. So you need to generate multiple clocks. Okay, so typically what we do, we split this requirement into two parts. One circuit is designed to generate a basic or a reference frequency, let's say a 40 or 20 megahertz, but an accurate reference signal. And another circuit which we called as phase lock loop, which is basically used to multiply this clock for various subsystems. Okay, so one of the very used circuit is like crystal oscillator. Crystals are basically quartz piezoelectric elements, devices which are normally put off chip. Okay, and they can be modeled as an RLC circuit. Okay, and the one thing is that they are very accurate. They are like less than for their frequency range, they are accurate of less than 10 part per million. Okay, And this is typically what goes inside the chip. You have an amplifier which powers the crystal, and which generates a sine wave, and then this comparator and buffer which drives the square wave output. Another example of clock reference generation is RC oscillator. Again, this is cheaper than a crystal, because crystal you need an external off-chip component. Okay, but this can be generated within chip. The trade-off is it will not be as accurate. After typically you need to do some kind of RC, post silicon RC adjustment, which we in industry call trimming, and the post trimming accuracy is roughly of order of ±5%. Okay, so there you have had a accuracy of less than 10 part per million. Here you have a ±5%. So the trade-off is again cost versus your application. If your application can tolerate this kind of inaccuracies, you can go ahead, because there is no need of external component, and it consumes another advantage is that it consumes lower power for same frequency output. So this is an example of one example of an RC oscillator. So this you can work out if you can work out this frequency on your own. That is the knowledge or skill level we'll be expecting. If you want to enter this area. So if you can work out that this will be kind of the frequency will be depend on this for it will depend on the RC component. Okay. The next thing is the phase lock loop. As I said, you need the phase lock. The first few slides I have explained you how to generate a clock. Okay, a reference clock. Now you have to multiply. Your chip needs 4 or 5 different frequencies. So there is a circuit which we call as a phase lock loop, which it is basically a feedback circuit, which takes the reference clock and generates a higher frequency or clock, or a multiple of input clock, frequency clock. So this is a typical block diagram of a PLL block. Okay, and output, if you see, if this is a basic. If you just ignore particularly right now the poles and zeros and other frequency element, the stability issue, you can show that this output clock is n times the reference clock if I divide the input by n. So by changing n, you can generate multiple frequencies. That's the basic idea. Next, I come to the very important thing is power supply. You need power supplies. So first thing, first I'm coming to the concept of voltage regulator. Basically, a voltage regulator is what? It should drive a constant voltage across load. Typically, what happens is that let's say a mobile phone or anything, these are battery operated system. Now, a battery typically, if you see a lithium ion battery, its output varies from 2.7 to 5.5 volt, right? And your core, digital core may be working at 1 volt. So you need some kind of interface, right? And second thing, you need some kind of interface, and you need some kind of constant voltage across to work for your system or SoC to work properly. So a typical voltage regulator is what? A typical voltage regulator generates a constant voltage across load current. So the very good way of understanding is through a resistor divider. So you have, let's say a 2 volt input, or I just make it to make it simple. Let's say you have 3 volt input and you need a 1 volt output. So through a resistor divider, you can appropriately get a 1 volt. But the problem is that your load current will vary depending on your, when you work, your load current will change. So conceptually, if I can somehow make this input resistance of the voltage source variable, so that my ratio always stays constant irrespective of R load, because R load will vary. R load will depend on the load current. Okay, it will vary, so that it can sense the R load and adjust R in so that output is always constant, right? That's the idea of a voltage regulator. So this is how it's actually implemented in practice. So this, this transistor, the PMOS transistor you see, is actually what I modeled as a resistance in the previous slide. Okay, and the other amplifier and the feedback loop actually adjusts this resistance depending on load current. That's how this voltage regulator works. So this I've just listed some building blocks of voltage regulator. A linear. This was an example of linear regulator. Sorry. Okay. Okay. So you need a driver transistor which is actually giving a variable load. You need a reference voltage, and you need an error amplifier and a feedback network. Next, I come to the very important topic of high-speed interfaces. So I believe everybody has used some kind of high-speed interfaces, either USB or HDMI. Okay, and of course these these are needed for these are used in commercial video, like for video or data transmission in a laptop or a phone for memory access, fast memory access with storage elements. Okay, so they are in reality very complex system. You need a very high speed protocol to there are actually high speed protocol and standards which are created to make system work seamlessly. So this is a particularly an example of a high speed IO, and if you see, even though for an user it will look like a digital system, in reality it is really an analog system, because you don't in an IO, because of an EMI issues, you really don't drive full swing 0 to for at least for high speeds. You don't really drive full swing. You have to drive you have to drive small signal, and if you want to constrain your system to a small signal, you have to use analog techniques to design those IOs. Okay. Okay, this slide actually I captured some of the challenges of designing high-speed IOs. So what I mean by jitter is actually uncertainty. Okay, so the challenge is that when you crank up speed, you should and it directly affects how much data rate you can support and send the data reliably. Okay. So this is I'm giving you an example of a typical SerDes block. You can call it a PCI Express or a HDMI or anything. So you see, just I wanted to capture the complexity of blocks. You have a protocol engine which has a standard, it showed standard. Then there are encoders, and from serializer, driver, and channel and the PLL from the transmitter side is basically a high-speed analog systems. Then you have and because these systems worked at gigahertz, so you cannot really model the output load as a lumped element, RC element. You have to take what are known and distributed RLC elements, which are technically known as transmission lines. Then at the receiver end, because once you send the data, there will be some droop, because there will be some loss in the signal. So you need equalizer, which kind of equalizer, and the thing is that in these circuits you cannot have separate clock path at that high speed, because the board skews will kill you. So you need to extract clock from that data itself. So there are specialized circuit called clock data recovery circuit, which works with PL, which extracts clock from actually the data. So whole thing, and these are again complex analog blocks, and then again it has to constantly interface with the protocol engine and deserializer, which are essentially digital blocks. So this is like this is reality. In reality, what happens when you transmit your data, you know, when you communicate with a typically with a USB or PCI Express kind of things. Again, this slide I have just kept to give you an example of how actually transistors are placed in analog design. So this is a picture of what we call a layout, which gives you a plan view of your design actually. So okay, from the trends in data, Abhinav will take forward from the no, Abhinav.
Yes, hey, thank you. Hey, thanks, Jadip. So I'm Abhinav Dikshit, and my colleague Jadip was calling from his home in Noida, and I'm calling from my home in Bangalore. We are going through some pandemic things. Interestingly, it's always good to talk to the people who really are here to choose what kind of career they want to pursue in future. And most of you who are connecting here, I presume that you are here to understand what it is like being an analog designer. In nutshell, if I could conclude what my colleague told you about some of the technical aspects of an analog design which you need to understand if you want to really uh, choose analog design as a career. And when I say analog design, it's actually we box analog design and RF design. Over the time, when you go in industry, you'll realize that analog and RF are kind of no very connected, but same time little different as well. It's definitely more connected than what analog and digital are, but little bit say different as well. So overall, uh, I'll say that means I assume that you most of you guys are here to understand what it will be, means why you should uh, choose analog design as a career. Okay. uh, you already know, if I could say that what Jaideep told, how it is little different from digital design, what are the important blocks, what are the fundamentals in the undergrad and post grad studies which you can actually focus on to become an analog design. But I'll talk a little bit about a different thing. It's about what lies what lies for analog designer uh, in the future, in the sense that means what you are expected to do generally as a job. And in one word, which if I can say, then it's going to be continuously pushing the boundaries. It's not like everyone else is not pushing the boundaries. Digital designers, DV, and layout designers are not pushing the boundaries. But as an analog designer, as an RF designer, you are expected to really continuously looking to make things better and better and better. Okay. And in if I really could tell means how you really do that is always over the time. You have already seen that Moore's law and continuous shrinking of the technology. We when I started my career, actually no I started working on 1.2 micrometer kind of technologies, and now we are talking about 16 nanometer analog designs, 5 nanometer analog designs, which actually our company is doing. Okay. What is expected means how you really push the boundaries of the performance of anything. Okay. Means as I said, that technology is at forefront. Shrinking down the technology is going to give you certain advantages and certain disadvantages when it uh, comes to performance or pushing the boundaries. In digital, it's very clear that shrinking down the sizes of transistor is a lot more advantageous than disadvantage. But in analog, it's actually entirely a different ballgame. It gives an advantage, it gives a disadvantage. Okay, so now you have to really evolve around the technology to ensure that you choose right architectures which are suitable for lower geometries versus the architecture which are suitable for higher geometries. So this is an added thing you have to really go through when you are choosing you have to continuously keep a watch on how technology is evolving, and same time how what all the architectures which are suitable for you know mm, for that particular design, specifically in analog. So how you do that? You continuously read about what all the things which are coming up, what all the architectures which are going, and I call it a collaboration model. Means you continuously uh, look around what your colleagues are doing, what other people in industry are doing, what academia is doing. So in as analog designer, you will spend a good time reading about what all the things which are happening around you. Means a lot of time, for example, at NXP we not only have a collaboration within the team, we have a collaboration models outside team, so within the company, and also there is a collaboration model inside industry as well. Means everyone really want to know where how other companies, other universities are pushing the boundaries. Okay, same thing is about no as an analog designer, I'll say that you'll never run away from your fundamentals. Okay, every time, even at 15 years, 20 years, 25 years of experience, people really go back and ensure that they have right fundamentals. Fundamentals are so necessary for analog design that you know if you have good fundamentals, you can actually think out of the box. So and pushing the boundaries in analog really require you to think out of the box. There's no solution off limit here. Means people really no go really imaginative when they try to solve a problem, try to make a smaller circuit, try to make a circuit which is a lot lower in power consumption, try to make a circuit which actually has highest efficiency kind of thing. So means I say that what Jadip was telling was a hard skill. What I'm telling is more like a soft skill. You have to you know you should means I have a formula. Like as analog designer, if you're not reading 15 to 20% of the work time, then you are actually missing on some of the best things you can do. So you need to be continuously reading about it. So all those who think that after this their graduation or post graduation reading is done, books are done, no, that's not going to happen for analog designer. You need to continuously be you know looking into the books, looking into the IEEE papers, looking into the latest trends. Okay, so mm, I'll say that uh, I'll with this as a context, I'll jump into what all the challenges analog designers have been facing, and how they are pushing the boundaries. So there are a couple of things which I'll talk, and then I'll keep it short so that I give more and more time for all of you to ask the questions, because you are here for your curiosity. Okay, so let's jump into it. So first thing I'll talk about is a data converter. So data converter is essential, as Jadip showed in a block diagram. Word is analog. Everything you see, touch, feel, or you want to control electronically, or you want to just process something, it's analog circuit. And word is analog, so analog designers are not going to go out of fashion ever. In fact, their challenges are going to increase more and more, because due to various aspects where electronics is the one which is doing something like all the way from medical to high speed communication, 5G, radars, and whatnot. So everywhere you need to first sense the environment, then you need to really control the environment. Okay, or control the outputs. So all these things need analog and data convert. But having said that, more and more content in the chips are going to be digital, and analog to digital converter, ADC, which you call, or digital to analog converter, are the interface, I say, between the real world and the chip world. Inside chip, immediately you want to convert everything to digital and do the processing. And we know the advantage of digital is it has very high amount of predictability, in the sense that when you really, design something and simulate something, there is a very, very high chance that it will work when silicon is created or chip is fabricated. But in analog, it all depends upon the skill of a designer as well. So apart from technology, apart from collaboration, apart from, your fundamentals, finally how skilled designer you are also determines how well you can push the boundaries. Okay. So in data converter, I said that, there are variety of data converter. In fact, when I was in my college at that time, I was thinking, why there are so many data converters? Just one data converter is good enough. But then the first thing it hits is data converter can go all the way from few hertz all the way to a terahertz. You are expected to burn current as low as 100 nanoampere for whole data conversion to all the way to 10 amperes. So and everything has a purpose. So for example, here in this thing, you can see that data conversion, some of the things which are sensor, which when I say sensor, it's like a lot of things which are being sensed around you. Okay, something like medical devices, something like your touch sensors, motion sensors, optical sensors, they all work somehow at human speed. So data conversion rate of of a lower frequency is acceptable there. Okay. But as you go into some of your automotive applications, their speed demand is high, and then you go to communication, it just goes berserk. Means it's like means there was a time when we never heard, but nowadays 10 gigahertz uh, data rate converters are also there, and in fact, even if you go to the lower number of bits, faster data converters are also there. So application wise, demand for different kind of data converters is there, and same time, it's not like a lower frequency data converter is less challenging and higher frequency is more challenging. The challenge is same everywhere. At lower frequency, you need a very energy efficient data converter, and higher frequency, you just need to push the boundaries, sometimes boundaries of the transistor, the speed at transistor can operate. Okay, let's move to next slide, Jaideep. Okay, so just talking about a system, it's more or less same as what Jaideep has shown in starting. It's like every system, including some of the most digital centric systems, also have something to sense. Then they do some analog processing, and then they convert it to digital, and then pass it to digital signal processing. The DSP here is digital signal processing. And finally, once everything is done, and functionality wise, the DSP, which is shown very small here, because as analog designer we see that small, but actually this is the 80-90% of the chip for some of the very high end digital centric products. And that output of that really fed back to a DAC, digital to analog converter, and then it becomes your, you know mm, something you hear, something you see, something you can, feel vibration of, something like that. Okay. uh, okay, so and here in this diagram, you can see that where are the different applications, and what are the signal to noise ratios which are needed from the data converters. So as I said, the signal to noise ratio is for a data converter is something which tells about, how accurately a signal can be converted into digital. Because every time you convert anything to digital, it's not one-on-one. There is some signal integrity will be maintained, but then it adds some sort of noise. So signal to noise ratio, and here it's mentioned in terms of dBs. So all the way from 30-40 dBs, which are typically, you can say, 8-bit kind of conversion, to 120-130 dBs, which are more like a very high 16, 20, 24-bit kind of conversions. So all things are needed. And then on the x-axis side, you see bandwidth. So bandwidth is essentially, you can say that at what speed these conversions need to happen in no layman's term. Okay, there's a lot more to it, but let's call it at what speed it need to happen. So you can see the bandwidth demand itself is touching few gigahertz now. Okay, means a lot of wideband application circuits where you can just directly put gigahertz data converter to solve the problem. And this all demand actually comes not always from the organic thing. It sometimes comes from just one brilliant designer thought about solving a problem of a system in a very different way, and he say, if I have really a very high speed data converter, I can really do something and reduce the overall system in a very small compact package. Okay, another thing, like for example, a lot of people think that, hey, if I can really have a very low data converter, like low power consumption data converter, uh, then I can actually put it somewhere in my with my let's say very valuable thing, or sometimes I can actually implant it with my pacemaker in my heart, so that for 8 years, 10 years, my data converter keep converting my activities into pulse, and actually and drive my heart pulse rate. Okay, so it's not that always it happens sequentially. So it's like, if someone can, means if you make these kind of things available in such a wide variety, then a lot of solutions can be thought about. So it's a combination of both. Okay, next slide, Jaideep. Okay, so I'm just telling you that how technology is really moving along. Okay, and these are one of the state of art data converters which NXP had created over the years. Okay, so these are the 2008, 2011, and 2013 data converters. You can see that how a high frequency 1.35 giga sample, uh, uh, you know 10-bit kind of data converter really was consuming just 175 milliwatt of power in 0.13 micron technology, and at that time it was big. Okay, and another example is that for 11-bit 3.6 giga sample per second data converter, uh, which actually it enables such a wide variety of solutions that maybe when I started my career, we never even thought that this kind of speeds can be attained. But you see, in 2013, in just 8-10 years, we were attaining these kind of speeds, and enabling so many expensive, many unique solutions. But let's see where we are today. This is 2013 to 2011, 2008. Okay, and I'll say that just keep in mind your 2008 1.35 gigasample 10-bit 175 milliwatt ADC. Okay, and if you go to next slide. Okay, so this is our recent 10-bit 1 giga sample per second ADC, which is more or less attaining similar performance than 1.36 gigahertz, little bit of slower in speed. But look at the power consumption; it's 7.8 milliwatt. Okay, it's ridiculously low. And if in 2010 also someone would have claimed that I can make a 10 bit, 1 GSPS, 1 gigasample per second kind of ADC in 7.8 milliwatt, we would have laughed. But see, this is a reality. We already have it at NXP. These kind of things, and means NXP, as I said, that is kind of running at the forefront of all the analog and RF technologies. Is the company which works on such a wide variety of analog, and then I'll cover that in later slides as well. But this is showing where technology has been, and how it is just pushed. It's just not uh, possible just because of very technology kept shrinking, okay, or like someone really was very careful in terms of design. It's just like you really start exploiting everything available to you around you, okay. For example, this thing is possible because of combination of so many things. Very innovative design. There's a constant demand push from customer or from application that, hey, I need a such a high speed ADC at such a low power consumption. And then there is a someone who could think out of box and say, hey, why not I use some of the digital techniques to make these kind of things happen. So I said that going forward, analog design is no more just a traditional analog design where you analyze your loops, you analyze your noises, you analyze your you know all the things which like your S parameters, your small signal models, and create a design. It's just whatever you can exploit, you should. And these kind of designs lately are just a combination of so many things, including some of the very high speed digital available, okay. So and low cost digital, like these days digitals in 130 nanometer versus like for example 16 nanometer digital area and power shrinks almost like 130th 140th, I don't know, means maybe a lot smaller than that, okay. So a lot of designs in analog are exploiting that as well. So it's just not pure analog, there's a lot of hybrid. We call it, that's a digital enabled analog, okay. And then you'll see there's not far away, there are a lot of people working on artificial intelligence enabled analog or some sensor enabled analog. So there's so many things which are needed, and just to make yourself aware of all these things, you need to continuously read it, okay. I'll actually next slide please. Okay, so another important thing, I'm not going to touch everything in every thing, but data converter is extremely important, and I'll try to close my presentation in next 5-6 minutes. So another most important thing you'll have is about power supplies, and one of the biggest problem with power supplies is there's a continuous power management, is there's a continuous demand for lower and smaller geometry, less and less I'll say source of power. And then you want to live your device for longer and longer. And cell phone, if you think was the challenging, then think about so many IoT technologies, and think about something like I told you, like pacemaker, okay, where there is a battery which has been implanted inside your heart through a operation, and it has to work for many years. You cannot really replace that battery every second or third month also. It's like 7 years, 10 years, and it has to be very tiny as well. So so here there are two examples given: WSN battery, solar cells, and tire pressure monitor, okay. Every whole system itself has to be so tiny that power supplies etc need to be very 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 small, okay. So next slide. Okay, so in every solution, what happens that I'll show that energy storage is very, I'll say one of the another challenge is energy storage is actually comes in a very standard format. Either it's nickel MH batteries, or it's lithium ion batteries, or it's something super caps kind of thing. and they all come in a very standard, voltage ranges. They are what they are. They are commercially available. Anyone can buy, and anyone can say, and they have been existing for like easily 30, 40, 50 years, and evolution in them, speed of change in them is very, very slow. But if you really see the application, next step, yeah. So if you really see the evolution in the chip industry, it's drastically changing. Means technologies and power supplies in 2000 versus 2020 have changed ridiculously, and even with 2010 to 2020 have changed ridiculously. For example, most of the analog now, which was earlier working on 3.6 volt, 5 volt kind of things, now works on 1.8 volt, and in fact majority of that works on 0.9 volt or even lower. Okay, most of the digital actually have gone all the way from 1.8 volt to you know uh, 0.4 volt. This is ridiculously low voltage to generate it. And then a lot of RF related stuff where you really transmit something in the air or in through a serial wire, they work still on very low voltage as well. Okay, something like 0.7, but battery supplies are same. And that's the challenge you will have in power management if you choose really to design a power management engineer. Okay, and in fact I'll say that over the time, so as analog designer, we start with everything, and over the time we dig deeper and deeper and deeper and become expert on one thing. For example, someone for very long time will become expert on power management only, because there's so much to explore, so many boundaries to push there, that he need to be a very deeply expert in just doing power management. And same thing with data converter. In fact, in data converter and power management, there are even in data converter there are champions of sigma delta data converter. They are champions of pipeline data converter. So this is how really career path chooses. And then if you go to next slide, I'll show that typically what are the conflicts and what are the choices you make. For example, let's say in power management, just to, as said, that real world has a very rigid approach that I need this kind of things only, I have this kind of things only. And then inside chip world is continuously changing. Okay, so then that throws some challenges, and to counter that challenge, there's like standard architectures which are available. But within those standard architecture, you can be very, very, very innovative. Okay, and solve the problem. So for example, here I show that just to convert the real world power supply to a chip power supply, there are three very standard approaches which are there. One is called LDO. Okay, it's like low dropout kind of regulator, and Jaideep talked about that as well. Okay, then other is called switch cap kind of circuits. Okay, where switch cap circuits. And then third is called inductor. So inductive kind of circuit. So everywhere it's all about ensuring you take one level of power supply and convert it to another level of power supply. Okay, but there are challenges. So for LDO, it's it its advantage with this is it is one of the I'll say lowest noise kind of solution, but it really has a limitations in terms of it can only convert from, let's say, 3 volt to 1.8 volt, or 1.8 volt to 0.9 volt, something like step down. It can only generate a voltage which is lower than the battery supply, okay, source. And while doing that, it's not even energy efficient as well. So sometimes it can be energy its efficiency is low. Okay, but it has a very good noise performance. Same thing if you go to switch capacitor circuit. So this is something which where there is a switching capacitor and keep dumping some charge on a big capacitor. Okay, and this actually what enables is so first problem is actually you need a one more capacitor, and not one more capacitor, it's a giant capacitor sometimes. Okay, so that even there are some current taken away from the capacitor, it's not, voltage is very steady and not fluctuating at all. Okay, and sometimes it, and most of the time this kind of capacitors often sit outside of the chip also. Okay, and that's inexpensive everything, because our, the challenges are to make system more and more compact, so everything need to be put inside chip. It has the advantage that actually you can create a step up and step down both. Means from 1.2 volt, let's say 1.5 volt battery, standard nickel like metal hydrate battery, uh, you can actually generate a 3.3 volt, as well as you can generate a 0.9 volt. So very good, but there is efficiency issues here. But same time, no, there are a lot of, I'll say, noise which comes in picture. So again, it's like designers have to overcome that. There are tricks and you can overcome. And third thing, which was one of the most standard things, was using the inductors property of storing an energy, and using that to generate a new voltage. And with doing this, you can generate step up, step down, and sometimes you can attain a very high, efficiency. But this also has, you know a problem, and problem is about, generating, problem is about noise generation. And also inductors often are implemented outside chip, which becomes a expensive solution. Okay, so next slide. Okay, so if you really see what all the boundaries we are trying to push here and how. Okay, so as I said, as a circuit technique, there are so many things, okay, which you do. But then there are technology enabler also, which are coming in picture. And based on that, you can also always define it in the sense of, no, how much efficiency you can attain versus what is the power density at peak efficiency. Okay, uh, so one of the challenges I didn't mention earlier was about, you know uh, today, the earlier solutions were there where, you need a power consumption, but peak power versus average power was like 8 times, 10 times, 6 times. Okay, but lately, because of the efficient compact system utilization, you need a very low ratio in peak power versus, average power, sometimes 2, 3, or even sometimes less than 2 also. Okay, so one of the parameters where you can actually really look at, how, where the boundaries are pushing, this chart shows. And as I said, that it's a combination of everything, how much, enabler technology is enabler. And you can see that what kind of, in next slide, that what kind of solid state technologies, yeah, this one, are enabling this kind of things. So you can actually do a lot of things within chip. I'm not going to go into detail, I'm running out of time here, so I'll try to close this thing. But it's a combination of pushing the no fabrication technology, and same time thinking innovatively. Okay, next slide. Okay, so quickly, I'll tell about the company here, NXP. As I already introduced, that NXP in industry is one of the leading, analog and RF solution providers uh, in the world. And if I my data is not wrong, then this has one of the most wide variety of solutions related to analog RF available. Okay, and you'll see one of the very interesting example later, that how the main means just a breadth of the product portfolio, along with the performance parameters, which are created, which for the technologies which are created by NXP, have been, generating a solution like futuristic solutions. Okay, but as a company, we are almost $10 billion revenue company. There are more than 10,000 R&D engineers, uh, you know it has 30 plus presence in 30 plus countries, and in fact you can say that there's a very active, deeply involved design activities going on in at least 12 to 15 countries, where actually someone like me have to really ensure that 12 to 15 different locations where someone like me have to really collaborate on daily basis. Okay, so very diverse company with a very rich history of product development and technology. Like there are more than 9,000 plus technology, and this is like old data. I think the latest is a lot more than that. Okay, next slide please. Okay, and as said that it's all about where all your solutions are, and these are just those places where actually NXP has a leadership position in automotive, in industrial and IoT application, in mobile and in communication infrastructure. It's not like NXP products are not being used in many other applications, other places also, but these are the places where our majority of revenue comes in. Next slide. Okay, and then I was talking about you know uh, how continuously pushing the boundaries in terms of performance, in terms of system thinking, in terms of innovation, and sheer in terms of capacity and breadth of product portfolio can enable a a futuristic solution. And one of the solutions is autonomous cars. Means in future you have means you are going to have autonomous cars which will drive themselves, but it's not like autonomous driving is waiting for the future. It's right now very much embedded in the current generation of cars also. It's at different levels. Okay, like there is something called level 1 to level 5 of autonomous driving, and the technologies need to enable that. Level 5 is little far, but we already have reached level 3, and someone is some car companies are claiming that their solution is level 4 as well. Okay, and how they are really created, for example, for autonomous driving kind of thing, you need variety of analog and RF centric solutions to come and solve the problem. There's no one solution which can go. For example, a radar is essential in solving autonomous driving problem, and we are a big supplier. In fact, one of the biggest, in fact the biggest supplier of the automotive radar right now in the world. V2X is about vehicle to vehicle communication, where vehicles will tell each other that, hey, I'm actually on road, please be aware, this is my speed. And also it makes solution very easy. ADAS vision is also, it's about bunch of cameras which are continuously looking into environment and ensuring that what signs are written, where is the next car, and all those kind of things. So there also NXP has a very strong presence. Then there is a LiDAR also. So and overall LiDAR also, which actually is kind of something in between vision and radar. And combination of radar, ADAS vision, and LiDAR and V2X, vehicle to vehicle communication, is something which enables overall sensing and awareness of the road conditions for an autonomous driving. But finally it all need to be come into, all the information need to come and need to be processed, and that's like a very massive processing capabilities. And not only massive processing capabilities, it also demands the highest quality and reliability, everything, because it's a matter of life and death for someone. Let's say, for example, there is a car ahead of you and your sensor doesn't work and doesn't tell there is a car, then someone can die. Okay, there is a kid on the road and your sensor doesn't really detect there's a kid on the road, then that life of that kid is under threat. So products are not only technology, but also there is a intrinsic discipline needed to ensure that we develop those products with the highest quality. And NXP being one of the it's not one of the, it's the top most automotive supplier, that also is kind of embedded inside our culture itself. Okay, so that's all from my side. And it's a time for question and answer. And question and answer, I think we have Jaideep and me, they both will take your question and answers. Over to Akhil.
Online or any hands raised. So before before we conclude the session, thanks Abhinav and Jaideep. And as before, we would be loading the videos and the presentation on our YouTube channel, and the link would be provided on LinkedIn. So the people who have been requesting for the presentation can view the presentations online. Our next presentation would be on 15th of December, and that would be on system engineering track, and that would be another very interesting topic that is going rounds right now in industry, and it is vehicle to infrastructure communication, or V2X as we call it. So stay tuned for all the updates on our LinkedIn page, and let us know your feedback, comments, whatever you may have, so that we can improve ourselves even more and make more technologically inquisitive presentations. Thanks a lot, everybody, and with this we end today's presentation. Thanks a lot.